Good afternoon, everybody. Welcome to another exciting afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. And since I'm Jewish, I have to say Happy New Year. Yesterday and today is Rosh Hashanah, the Jewish New Year, and the traditional greeting is Lashana Tov. Actually, it's much longer, but it's been shortened down. The Yiddish greeting is Good Yontif, and I hope you all have a healthy and happy New Year and prosperous one, which is also a traditional greeting. Hopefully, you had a nice Labor Day weekend. I went to war with my lawn, but first I had to fix my lawnmower, and I did, and I've had it over more than 20 years. But that's the joy of knowing how to use tools and doing maintenance on things. All right, couple things. First of all, I was looking at the schedule, and I do it every fall. I think I can get all of it in, and I could, but that won't be fair to you. So I'm probably going to be postponing test number one by 1 week. If you look at the syllabus, it's supposed to be next Wednesday. Well, yeah, I could rush and finish everything up by Monday. That's not fair to you. So I'm going to probably postpone it. I'll put out an email by Friday, which I probably will. So, anyways, that's that. The other thing I couldn't remember and I didn't know, but I figured you might have forgotten too, since I might have. On Monday, not today, but Monday, I'll go through the alkene and alkyne practice problem set. I'll do that on Monday. So in case you, excuse me, if you had decided to enjoy Labor Day weekend and you haven't had a chance to do it, you got plenty of time to do it. All right, today we're going to have not only lecture, but we're starting to have labs. And I'll talk about that later. All right, let's get going. Now, I finished a chapter on alkenes, and it's new chapter time. And that new chapter is aromatic compounds. Everybody see that on your screen now? Thank you. Thumbs up, people. All right. Now, aromatic compounds are named aromatic compounds because they are originally organic chemicals or compounds isolated from spices and herbs. Vanilla is an example of one. Another one, it's called raspberry ketone. The taste of raspberries is because of an aromatic compound. And there are a number of them. I'm just a vanillin freak. I love the taste of vanilla. And aromatic compounds were found to have unusual chemical properties. They were especially stable. Many of them, this should be really C6H5 ring, but have what's called a benzene ring in it. Now, quick little thing I thought I'd show you. There's a great book I found out about this a number of years ago, and it's about time for me to reread it. Every good books I really love, I reread every couple of years, just in case I forgot something good, and it's fun to go back and reread a good book, sort of like visiting an old friend. This one's called Napoleon's Buttons, How 17 Molecules Changed the History. Now, why is it called Napoleon's Buttons? Well, I don't know if you call it an urban myth. Is it true? People really don't know, but it has factual possibilities. I'll put it that way. Why did Napoleon lose when he entered Russia? Not only the weather, but because of the weather, the metal, the buttons of his army's coats were made out of a metal. Here they say tin. I'm not sure if that's that or bad tin. And when it gets super cold, drops to below 56, I think that's minus 56, the buttons become friable. Friable is a chemical term meaning it crumbles like this. And if you're trying to fight a war in super cold weather and you can't keep your clothes, you're going to have trouble fighting. Is that true or not? I don't know. But the important part of Napoleon's Buttons, one of the great chapters, this is a really fine book, is that major wars between the major European countries back in the 14th, 15th, 16th, 17th centuries, even a little later, were fought over aromatic compounds. Wars over aromatic compounds, and we call those the spices. I think you're all familiar with how America was discovered, quote unquote, by Christopher Columbus. If you believe the Vikings were here first, which I do, I'm a Viking freak. I've been that way since I was about 10 or 11. But anyways, Christopher Columbus was looking for a shorter route to India because of the spice trade. Aromatic compounds. Obviously made a wrong turn and came here. But aromatic compounds played a tremendous role in our daily life. Now, when we talk about aromatic compounds, the simplest aromatic compound is called benzene. And it switches off for this slide, the next one. And whenever you say benzene, one of the greatest of all chemists, I don't know if they were called organic chemists back then, but he was an organic chemist, was the Austrian, I think it wasn't part of Germany then, or chemist, Kekule. And he's one of the greatest that I have down here, organic chemists. And he was the first one to propose a reasonable structure for benzene. That alone is a lifetime achievement. Now, when you say Kekule, any good organic chemist will immediately think of Kekule snake dream. Snake dream. Well, later on in life, he actually came up with the first concept or structure of benzene when he was in his, I think, 30s or 40s. Well, later on, when he was near the end of his life, he was at a symposium or a lecture he was giving, and someone asked him, how'd you come up with the idea for benzene? And he said, the night before I came up with the idea and knew I was right, I had a dream. And that dream was a snake chasing its tail. And finally, it bit its tail, so it was a circle. And that's how I came up with the idea for benzene. Now, that alone would be a lifetime achievement, but a few other minor things, not really, that Kekule came up with, and again, switches off on this slide. He was the first chemist or scientist, one of the first to recognize that carbon should have 4 bonds to it. By the way, I use this every once in a while. IE is short for that is, I forgot what that means in shorthand for Latin. And that carbon is tetravalent. In other words, 4 bonds to carbon. And he was also one of the first to recognize that carbon atoms are connected together by chemical bonds. Those are all lifetime achievements, but he's most known for developing that benzene contains 3 what we call conjugated double bonds. The word conjugated means alternating single, double, and so on. Now, here's a picture of Kekule on a stamp. It's from DDR. If you don't know what DDR is, that's Deutsches Demokratische Republik, otherwise known as East Germany, which is no longer. And they show him, great beard. I love that beard. I got to keep my beard short because when I go into chemical plants, if I ever have to wear a gas mask and you have a beard like that, you'll be dead. But anyways, great beard. And here's the structure of benzene. And notice he lived in the 1800s. And I actually took about 3 years ago, whenever I show this picture, I tell students, if you ever see this, let me know if it's reasonable, I'll buy it. And a Chem 170 student emailed me and said, I saw it's for sale on eBay. And lo and behold, and I don't have it with me right now, but downstairs frame, I bought 2 of them. They weren't that expensive. I was surprised. And now I'm a proud owner of this stamp. Now, when we talk about benzene, let's see, let me go a slide. Kekule came up with the structure, and benzene is like this. Let me check something. Yeah. Let me skip this slide and move on to what's called the orbital model of benzene, which is still off, but we have what's called p orbitals and sigma orbitals. And like the two sigma p orbitals come together to make a pi bond. And in benzene, here you have 6 carbons in a ring. Each one has an electron in the p orbital. And if you have overlap, which you do, they share electrons. Think of it, have you ever seen kids play Ring Around the Rosie where they're all holding hands? Well, that's what all the carbons do in benzene. And the sharing calls or forms on the right here the pi bond that's spread around all 6 carbons. Now, if you look at it a different angle, what Kekule came up with the idea of how to show this, and now the switch is on. Let's look at benzene. Now, if you look at the p orbitals, there are 6 electrons. 6 divided by 2, remember, takes a pair of electrons to make a chemical bond, like a pi bond, is 3. So one way of drawing benzene is this way. Now, you can move the electrons here, here, and here. And if I draw that, it will look like this. And no, I haven't. Let's call this one, this one. I've just moved the chemical bonds. Well, they shift back and forth or exist as both. And we show that by a double-headed arrow. And we call that resonance. And those are the resonance structures of benzene. And these are called the Kekule structures. Now, another way of drawing benzene is to, if you look at the slide I had, which we can do that, if you were here and you were looking from the top down, what you would see looks like a donut. And the way to draw that, and it's called the pi delocalized structure, is this way. Six-membered ring, and then a circle. That's what you're looking down at. Now, this is called the pi delocalized. I personally like the Kekule structures. I just think they look neater. That's my personal opinion. So if I were to ask, draw the structure, of benzene, it's the simplest aromatic compound. There are 3 different ways you could do it. Generally, I do this way or this way, or you could do this way, which on a test would be totally correct, but I like these better. I just think they look cooler throwing the double bonds in there. Notice the 2 structures on the left have conjugated double bonds, 3 of them. Double bond, single bond, double bond, single bond, double bond, single bond. And that's the structure of benzene. It exists as both of these at the same time, or you can just draw it like this with a circle in the center. Now, if on a test, and listen carefully, I ask, draw the structure of benzene, and you do that, you're wrong, because that's cyclohexane. And students always say, well, can I get partial credit? And I always answer, if I ask, what does the sky look like when the sun comes up and there are no clouds? Is it dark or light? And you put down dark, you can say, well, shouldn't I get partial credit? No. Or if I ask if you're if on a test you're asked to draw the structure of a hand, outline of a hand, and you do a foot, should you get partial credit? No. Well, they both have 5 digits. Remember, benzene, put the bonds in or use the circle to show the delocalized pi cloud. I like the 2 on the left, which is what I'll do in class. But if you ever want to do this one on the right, it's correct also. But if you don't have anything inside, it's cyclohexane, and this is not benzene. Now I come back to here. Here I show you the delocalized or the resonance structures. And back when I made this slide, I put brackets. You really don't need the brackets. You can't isolate one or the other. They exist both at the same time. This is a chemist, organic chemist way of visualizing it. It's really like this right here, where they're all holding hands with pi electrons. And the single bond is between there. Now, switch is definitely off on this slide, but the reason I put this on, I've been told some standardized entrance exams that test you partially on organic will ask this question involving this. Now, I have written here cycloatomic, and I'll teach you later on. You can have one of those atoms later in the semester as nitrogen or oxygen. But for now, when you have a carbon ring, it has 2n plus 2 pi electrons, that 2n plus 2, or n is the whole number, equals the number of pi conjugate electrons, then that's called aromatic. This will never be on a test of mine, but somebody says, if you have a ring with so many pi electrons, is it aromatic or not? And you use this formula. But if we look at benzene, each double bond is 2 pi electrons, so it's 6. And when n is 2 equals 6, so benzene is aromatic. But again, I'll never ask on a test or a final. And notice that once again, here's one Kekule structures. You could also write it this way, which is another what we call resonance form. And that's how you can draw or write benzene. Again, I like Kekule structures. I just think they look cool. Now, let's talk about the nomenclature of aromatic compounds. Now, it turns out benzene has been around here for eons. I mean, eons. And IUPAC, in their infinite wisdom, and this isn't the only time they've done it, is say, well, we've been using this name for this compound for generations. We're not going to get those organic chemists to change. So we'll just use what's called the common name. Names of chemicals before IUPAC. Remember, IUPAC is the organization set up by a treaty back in the 1920, give or take a few years, that is the referee, so to speak, or the organization that came up and referees all names of chemicals, and most of them are organic. So they made the common name the IUPAC name. So this molecule, the IUPAC name is benzene. And you should know that. Switch is on full blast. So benzene, 6-membered ring, And don't forget the double bonds in there. Now, when you put a methyl group on benzene, no, we don't call that methylbenzene because this molecule has been around for eons, and its common name, toluene, was also made the IUPAC name, and you should know the structure of toluene. Now, one, I'm not going to ask you, but we find a name in our common vocabulary is when you have a double bond attached to benzene ring. The common name, which has become the IUPAC name, is styrene. How many of you have ever heard of polystyrene cups or polystyrene coolers? Have you seen those, the white plastic cups that you put hot coffee in that you might get at certain places? And that's made from this chemical. That's why it's called polystyrene. We'll talk about it later in the semester when I get into polymers. But you should know the structure of benzene and the structure of toluene. Now, I have some sort of a sad story to tell you. The truth about benzene and toluene. Both are liquid at room temperature, and they've been used as solvents in paints. They don't use it anymore, but they used to. And benzene and toluene, when you inhale it over a period of time, it destroys various organs in your body. And not being a medical doctor, I'll use the term, and it rots out your brain. It's a dangerous, hazardous chemical, both of them. Now, how many of you, don't raise your hand or anything like that, have ever met anybody or heard about people who sniff glue? And those glue sniffers, they'd sniff it, and supposedly they get a high out of it. I don't know. I've never done it, never will. Don't know anybody who has. And that causes the high is toluene or benzene and the stuff they're sniffing. Glue, like airplane glue used to, I don't know if it does now, have toluene in it, and people would sniff it. Now, for till about the 1960s, give or take a few years, paint used to, before what's called latex paint, which I'll teach you about later on this semester, had as a solvent benzene or toluene. And painters inhaled a lot of it. They didn't know it was dangerous. And when I was about 10 or 12, a cousin of my mother's, I knew and met a number of times. He had been a painter all his life. And by the time I met him, he was in his early 60s, I think, maybe even younger. And his brain was gone. He was about one step up from a vegetable. It was very sad, but that's what the hazards of toluene and benzene can do. But still a useful chemical when handled safely. Now, when we talk about benzene, we can use numbers, but benzene has something interesting when you have disubstituted benzene. And I'm going to turn the switch full on. And bear with me. If we were in a classroom, you'd be watching me write this on the whiteboard. Now notice I have 3 isomers of the same, with the same empirical formula, same number of carbons, hydrogens. And notice the first one, and I'm going to go to Technicolor, is 1,2 disubstituted. The second one is 1,3 disubstituted, and the last one is 1,4 disubstituted. Now, they're all ethyl and propyl benzene. And you would have been watching me write that on a whiteboard too. Now, it turns out somewhere, and I've never really tracked down when or who came up with this, for only disubstituted benzene, we have some, instead of using 1,2 ethyl and propyl, organic chemists came up with the following. When you have 1,2 disubstituted, it's called ortho. 1,3 is meta. And 1,4 is para. Therefore, the first one is 1,2, so its name is ortho ethyl and propyl benzene. The root name is the ring, benzene. By the way, a common mistake I see on test number 1, so please don't do this, is somebody puts down, oh, it's 3 double bonds, 3 is tri, double bond is ene, cyclohexatriene, no, that's benzene. Now, number 2 is 1,3, so this would be meta ethyl and propyl benzene. And 1,4 in number 3 here would be para ethyl and propyl benzene. So on a test, if I were to ask if the IUPAC name for number 1, it would be ortho ethyl and propyl benzene. Organic chemists for benzene rings do not use numbers. They use ortho, meta, and para. How many of you have ever heard of Ortho Pharmaceutical Company? I wonder where they got their name. All right, let's take a look at one. And the question would be, give the IUPAC name for the following. And the first thing, look for what's there. Ooh, what's not a carbon-carbon single bond or carbon hydrogen? I see 3 double bonds in a ring, and that's benzene. This is a benzene ring. And then on one carbon of the benzene ring, I have an ethyl, 3 carbons to the center carbon, is called isopropyl. If I could spell right. After Labor Day, my spelling goes downhill. If you believe that, I got a bridge in downtown Chicago, I'll sell you cheap. So it's ethyl isopropyl benzene. Now, notice it's one carbon, I'll call one, the other three, doesn't matter which one of those you call one or three. So it's 1,3-disubstitute. And if I scroll up, oh, look, somebody put a nice chart on here. And 1,3 is meta. So this would be meta-ethyl isopropyl. Now, there's one other one I need to show you. Now, a methyl group on a benzene ring is called toluene. And even though it's part of the name, that methyl group is considered a substituent alkyl group on the benzene ring. So if I were to do this, even though toluene covers the benzene ring, six-membered ring, with the double bonds in the methyl group, this is considered a disubstituted benzene. So how do you name it? The root name is not benzene, it's toluene. That takes care of this methyl group and the ring. But now I have this substituent, which is ethyl. And technically, or not technically, to name this, this is considered a disubstituted ring. And you use ortho, meta, and para. Now, in toluene, the methyl group is 1, so the ethyl would be on 4. So it's 1, 4 disubstituted. And if we come up to our chart here, 1, 4 disubstituted is para. And therefore, this would be para ethyl toluene. Again, when you have a methyl group on benzene, it's called toluene, but the methyl group is still considered, even though it's part of the root name, still considered a substituent on the benzene ring, so we use ortho, meta, and para. Now, if you have more than two substituents, then we use numbers. We'll get to that later. And it's time for you to have some fun. And the question would be, what would be the IUPAC name for that? I'll write this chart. Ortho 1,2 disubstitute, meta 1,3, and para 1,4. In case you forgot, when you're done, give me the thumbs up signal. Thank you. I see thumbs are coming up all over the world. And I think everybody's done. So let's do this. What do we have that's different? Ooh, a ring, but it's got 3 double bonds. That's benzene. And we have 2 substituents, ethyl and butyl. Now, if you put the ethyl first and the N-butyl second, remember, I'm not holding you to that alphabetical rule, so I would count that correct. And notice if I call one, one, the other is two, 1,2 disubstituted is ortho. Oh, this is fun. So this would be ortho N-butyl ethyl benzene. Let's do another one. And there you go. What would be the IUPAC name for that? Remember, methyl group on a benzene is toluene. Oh, this did something. I might as well share a secret with you. If you have glasses, I don't know if all of you are wearing glasses or any of you, and you got your lenses made in the last couple of years where it's got the new coating on, where they give you that cloth to clean them from your optometrist or wherever you buy your lenses or glasses. I get mine at Zennies, most of them. This I didn't, but usually I do. If you go to Walmart, they sell microfiber tiles. I think it's 3 or 4 for a couple dollars, and they make great glass cleaners. Just as good as what the optometrist gives you. All right, let's do this. What do we have? Benzene ring with a methyl group. So we call that toluene. And then 1, 2, 3, 4. We have a, I'm going to start calling it T-butyl because I'm going to be able, instead of tert-butyl, but you can put either one down, a T-butyl group, and on 4. And if you don't put the hyphen there, I don't even know if it should really be there. It's a bad habit of mine. And 1, 4 would be para. So this would be para T-butyl toluene. And that's how you do it. All right, I'm going to write down 1. And don't forget, I haven't said it, and it's been a while since we've been together. Don't forget, there's no such thing as a dumb question in my class. Always feel free to ask questions. Now, one question which happened in my other class, which students said, in my office hour, they asked me about if I could help them. And I said, sure, ask me during class. I have the fastest mouse wheel finger this side or the other side of the Mississippi. If I move too quickly, always feel free to ask me to come back, move back to that last slide or whatever I was doing. And the answer will always be, of course. Now, this one you don't have to write down, but I can't resist. Again, you don't have to write this down. Does everybody know what that is? Can you see the structure? Of course, it's paramedic. 1,4 disubstitute para. Oh, by the way, it's permitted to moan and groan and boo in my lab, my class or lab. Not too loudly though. All right. Now, if we look at a structure, we can draw the name or write the name, but here's the name. How do you draw the structure? No, I don't want to do that one. Let's do this. Ooh, here's one I haven't done. And the question is, how do you draw meta-diethylbenzene? Well, you start from the right and move left. As soon as I see benzene, don't forget the double bonds in there, 3 of them, and they're conjugated, alternating single, double. Or you can just put a circle in there, but I like this way, it's cooler. Then I have ethyl, CH2, CH3, di means 2, and meta means 1, 3 disubstituted. So I have 1 ethyl group, and I count clockwise or counterclockwise. Both of you are going to go clockwise. I have my other ethyl group, and that's how you decode the name. And it's your turn. Draw the structure for orthoethyl isopropyl benzene. Have fun. And when you're done, give me the thumbs up or a high sign. For those of you who've ever seen our gang, the high sign. All right, I think everybody's done. Let's do it. The question is, how do you draw this structure? You start from the right, move left. Benzene ring. Don't forget the circle or the double bonds that are conjugated. I have an isopropyl and ethyl. Now, most of you are probably going to put the ethyl group here. Doesn't matter. You could have put the isopropyl. This is 1. Ortho is 1, 2 disubstituted. Therefore, this is 2. Isopropyl, 3 carbons. Center carbon is bonded to the benzene ring. And something I forgot to do. Oh, no. Don't forget, there's always 4 bonds to carbon. And that's how you do nomenclature for disubstituted benzene. Now, before I go to other substitution, I've done the ortho, meta, and para. Let's talk about some more substituents that you should know. And when you have halogens on, this also, they can be used for alkanes and cycloalkanes, but I decided to hold off until benzene rings. When you have a chlorine atom on a benzene ring or anything else, we call that a chloro group. Bromine is bromo. Iodine is iodo. Fluorine is fluoro. Now, a very important group, NO2, where the nitrogen is bonded to the benzene ring, or it could be just cycloalkane or alkane. That's called the nitro group. Now, these for chloro, bromo, iodo, fluoro, and nitro, you should know the structures and the names. Now, there's another one we'll talk about later on, which I'm not asking you to learn now, is sulfonic. And sulfonic is S sulfur with 3 oxygens. One of the oxygens also has a hydrogen. This is called the sulfonic group. And that group on a benzene ring with some other stuff is responsible for the main molecule in 90% of all laundry detergents. And if you're asking, why am I learning this stuff? Well, guess what? It's important if you like clean clothes, because a derivative of a benzene ring, something made from a benzene ring with this group, has been used since about the 1950s and to this day as the key ingredient in laundry detergent. Now, just like on a cyclohexane ring, when you have one substituent, you don't use a number. So what would be the name of this compound? I've got a benzene ring. And this is bromine, which we call bromo. So that would be bromobenzene. And why don't you try this one? What would be the name of that? And let me bring up the other screen. First of all, everybody have that written down? And let me bring up the other screen to help you out. And why don't you name that? In fact, I'll write it right up here. When you're done, give me a thumbs up. I guess you if you have your webcam on, you can do a thumbs down, but don't please. All right, everybody's done. What do we have here? Well, this bond looks sort of funky, even still looks funky. Let me fix it up. We have a benzene ring. And here we have Cl is chloro. And that would be chlorobenzene. Now, if I look at the clock, it's time for a break. So come back at 1:55. We'll continue with this, and then we'll do our first lab. I'll see you in 5. time to get going. All right, we were talking about nomenclature of aromatic compounds. Oh, that reminds me, we talked about vanillin. One of my favorite places, I used to go there, but after the pandemic started, I just order online. It's in Evanston. I think they have one in Chicago and one in Milwaukee. And I don't get any kickbacks. It's called the Spice House. And it's, like I said, there's one in Evanston, one in Chicago. And one of my most favorite things, I love the taste of vanilla or vanilla. And this Madagascar pure double strength vanilla extract is the best vanilla extract you'll ever buy. Once you taste this and use it, you'll never go back to the garbage they sell in the supermarkets. But it's expensive, but it's worth every penny. A 4-ounce bottle is almost $43, but it's double strength and it lasts a long time. I'm a vanilla freak, so I'll buy it. Looks like they're out of stock right now. It's sold out, but when it's in stock, I buy the 8-ounce fluid ounce. And yeah, it's expensive, but oh, it's so good. Now they have other great things here, and I'll talk more about it later this semester. But one of my favorite here is their Mexican spices. And this one is my all-time favorite. They're ground chipotle, and I go through this a lot. And their cumin and other things are really good. And they have 3 different chili powders, regular, hot, and real hot. I get the real hot. Yeah, is this too hot? They also have something very dangerous called ground habanero powder, which is super hot, but once you learn how to use it, it is awesome. All right, let's get back to nomenclature. Remember, new substituents, Cl chloro, Br bromine, I iodo, F fluorine, NO2 nitro. Now, you can have disubstituted of these. And if we look at that, what do we have? We have a benzene ring. And what do we have on there? 2 substituents. This is a chloro, this is a nitro. Now, since I'm not holding you to the alphabet rule, you could have put nitrochloro, but this is the right way. This is 1, 2, 3, 1,3 disubstituted, which would be meta. And that's how you do that. And why don't you try this one? Meaning give the IUPAC name for the following. And by the way, you're free to show my, which I didn't come up with, parajoke, paramedic to anybody you like. And over the years, more than once, like this last summer, I actually had a paramedic. Oh, I've got to show my whole firehouse that. I've got 1 thumbs up. 2. If you're not finished, I'll give you time. And there you go. Let's do it. What do we have here? We have, iodine, iota, NO2, nitro. So this would be benzene ring. And notice this is 1,4 disubstituted. Where do I get that? I count carbons, 1, 2, 3, 4 on the ring. 1, 4 is para. So that'd be para-iodo-nitrobenzene. Now, there are 2 skills you should have in organic chemistry when it comes to nomenclature. One is, here's the structure, write the IUPAC name. The other is, here's the name, draw the structure. So let's try one. And you know something? I think you're up to the task. Let's see if you are. Why don't you try one all on your own? How would you draw meta, bromo, chloro, benzene? Remember, ortho 1, 2, meta 1, 3, para 1, 4, disubstituted. I see 1 person, 2. I see your thumbs up. And almost everybody's done. All right, let's do this. How do you decode this? You start from the right, move left. Benzene, 6-membered ring with 3 double bonds, or you could do the circle. I don't. I have a chloro and a bromo. Chloro is chlorine, bromo is bromine, and it's meta, which is 1, 3. Well, it doesn't matter which one you put. I could have done this as 1, 2, 3. I could have just as easily done this. And there are other ways. All I'm doing is rotating it. One of the things which people tend to forget and that is molecules we draw on a piece of paper are not glued on a piece of paper. Just like your hand, if I were to say, close your eyes, I went like that and say, oh, look, it's another hand. No, you just rotated 90 degrees. Or if I said, here's my left hand, close your eyes, and I went that while your eyes were closed, I said, oh, look, something different. Said, no, you just rotated 180 degrees. Well, you can do that with a benzene ring. That's why there are different ways of drawing it. Now, when you have more than, I don't really have a slide for this, when you have more than 2 groups, you use numbers. And let's look at the following. And the question would be, what's the IUPAC name for that? Base name, benzene ring. Look for what's different. Next, I have a bromo, and I have not 1, but 2 chlorines. So I'm going to call this 1. This would be 2. This would be 3. that would be 4. So it's 1 bromo, 2, 4. When we have 2 of something, we say dichloro, and it's benzene. Again, and now there's other ways you can number it for you, but this is the right IUPAC. If you put the 2,4-dichloro first and the 1 bromo second, I would not mark it wrong, even though it would be wrong by the IUPAC rules that I am governed by. All right, let's have you try one. All right, why don't you try that one? What would be the IUPAC name for the following? Well, 2 people are done. All right, let's go ahead. First of all, I say a 6-membered ring with 3 conjugated double bonds. Remember, conjugated, double, single, double, single, double, single, alternating double and single. And that's a benzene ring. Then I have a bromo group, a nitro group, and a chloral group. I'll call this 1, 2, 3, 4. So it'd be 1 bromo, 4 chloro, 2 nitro, benzene. Let me write it better. And that's how you do it. Now, if you had 4 chloro, 1 bromo, 2 nitro, that would be okay. If you numbered it slightly, well, no, actually, let me show you something. When you're numbering the substituents, you do it in such a way that you give all substituents the lowest number. If I had made this 1, this would be carbon 2, this would be 3, this would be 4. So it'd be 1, 3, 4, which is larger numbers than 1, 4, 2. And that's how the IUPAC. Now, if you had done it the other way, I'd still give you credit because I'm not holding you to the numbering on a ring. Oh, let me do one more for your enjoyment this afternoon. And I'll do this one. And the question would be, what's the IUPAC name for that molecule? And I'll do it. But first, I'm going to get a drink of water because my throat's telling me to. Well, oh, I got a benzene ring, but I have a methyl group on it. So that's toluene. Oh, nitro group, a second one, third one. Remember, di is 2, tri is 3. So that would be tri nitro toluene. And notice that this is 1, this is on 2, 4, 6. So when you have tri, you need 3 numbers. So this would be 2, 4, 6 trinitrotoluene. 2, 4, 6 trinitrotoluene. Did I tell you organic chemists are lazy? 2, 4, 6 trinitrotoluene. That's hurting my jaw. Ouch. So why don't we just call it TNT? That's not the IUPAC name. How many of you have heard of dynamite? This is the key molecule in dynamite. TNT, trinitrotoluene. Actually, 2, 4, 6 trinitrotoluene. Now, how many of you, and give me a thumbs up if you have, how many have heard of the Nobel Prizes? I would think most of you have. And who started that? Alfred Nobel. And guess where he got the money to set up the Nobel Prizes? From something he and his brother discovered or invented. Now, 2,4,6 trinitrotoluene is a liquid like this. If I were to go like this with 2,4,6 trinitrotoluene, you wouldn't be seeing me anymore. You wouldn't see my home anymore because it would have blown up. It's very shock sensitive. And to use it was very dangerous, especially when you had wagons pulled by horses. They would blow up once in a while, sad but true. They found a way of stabilizing 2,4,6 trinitrotoluene to use it in explosives. And one of the ways in dynamite is, and I don't know the whole formulation, it's not an area I've worked in, is to mix it with clay. And that helps stabilize it. So you use a blasting cap to make it blow up. Well, also because of that, they could use 2,4,6 trinitrotoluene, stabilize it, and use it in various munitions for armies. And the bulk of Alfred Nobel and his brother's money came from selling their products to armies of the world for wars. So the Nobel Peace Prize, Nobel Chemistry Prize, and medicine, and I think there's another one, but I can't remember, physics. I don't know if there's one in literature or not. They all came from the money set up from profits Nobel made from selling explosives to military for war, bombs, and other things like that, hand grenades. But there's nothing wrong with that in my mind, but I thought you'd know about that. Now, there is a sad part, and maybe why he set it up. You might want to look at. I've heard pro and con, is this true or not? Why he set it up, but what I will tell you is true. Even then, it's still dangerous handling trinitrotoluene, 2,4,6 trinitrotoluene. And unfortunately, tragic accident happened at one of their plants making explosives, and it blew up, and it killed Alfred Nobel's brother. And did he do that for his brother or because he wanted to be known throughout time and set it up? Don't know, but he did use the profits from selling explosives to armies of the world to set up his Nobel Peace Prize. All right, now, when you react benzene or look at benzene, there's something called, and the switch is off for the slide, resonance energy. Now, when you look at benzene, you say, oh, look, it's 3 double bonds. If I react it with hydrogen, I should be able to get rid of it, but you can't that easily. Remember, double bond, hydrogen, and a catalyst, you break the pi bond, each carbon gets a hydrogen. But you try and do that with benzene, even if you use excess because you have 3 double bonds and a catalyst, it's really hard to do that. And it doesn't react like it's 3 single double bonds. There's something different about benzene and aromatic compounds. They don't, yes, you can, but you really got to heat at very high temperatures. In organic chemistry, if you're industrial organic chemist, you really got to beat on it to make it work, where normal hydrogenations, you don't. And what's that difference? It switches off for this slide, but you should know about it. That's called stabilization energy, or as I like to call it, resonance energy. And that's the difference between the energy of the real molecule and the calculated energy of the most stable contributing. Now, if you took benzene and you can measure its energy, if you took cyclohexane and measured also 3 double bonds and added together, normally you get a close number. Here, this is way lower, meaning more stable. What does that do to resonance energy? And what do we mean by that? When I can draw resonance structures like this, oops, same thing. This is a resonance structures. And whenever you can draw resonance structures for a molecule, it's more stable than the theoretical doing it by this calculation. And that means you don't break carbon-carbon double bonds in a benzene ring easily, usually not at all. Oh, if I look at the clock, guess what time it is? It's time for the lab. So if we had been in a lecture, which I would have gone like I usually do, I'd say, let's take a couple-minute break, what we just did, so I won't do it now. Then we go over to the lab and have our lab. Well, we're not going to go to the lab at ECC. We're going to have it online. Now, let me mention something I didn't when we did syllabus, and I don't have it open, so I better open it up. All right, everybody should see the lab course syllabus for this class on the screen. Now, we're going to be doing labs. Really, normally you'd go into lab and manipulate things by hand. Unfortunately, with the pandemic, I'll show you how to do things, but you'll be interpreting it. You'll get the same mental exercise as if you were in my labs face to face. Now, each lab is worth 11 points. Now, we're going to do 13 labs, and the way I do it is when we're face to face, what happens if a student's sick? Well, they missed the lab. Should they get a 0? No. So what I did was, we'll do 13 labs, and the 12 top of the 13 will be added together to get your lab total, which, as I mentioned earlier in my syllabus, your lab plus your 3 highest tests plus your final plus an extra credit divided by 632 gives you a percentage, and that determines your grade. Now, important thing, labs are due the next lab session after the session. The lab report being handed in was done. I should have added here was done. And therefore, the lab today will be due next Wednesday. And that's how I do it. Now, if you don't hand in the lab, you get 0 points. Simple as that. And if you hand in a late lab, you'll lose 2 points. If your lab is more than 8 days late, like if it's due next week, and you wait another 8 days, you get 0 points. I put that in so I don't, at the end of the semester, have all the students start handing in 10, 12 labs. That happened one semester with 2 students and 170 until I put that line in. Now, here's the labs, and in face-to-face, guess what? You don't have to buy a lab book. When I took over this course, I took it over and the labs were beyond awful. They were beyond pitiful. And part of the problem with this class is if we were face-to-face, the lab is only an hour and 50 minutes. Other schools, the lab is 2 hours and 50 minutes, so almost 3 hours. Where here I only have a little less than 2 hours. So I can't use traditional lab books for organic because most of those labs are anywhere from 2 hours and 15 minutes to almost 3 hours. So I came up with my own labs that teach a lot of the stuff other labs do, but they're shorter and get you out in an hour, 50 minutes. So that way students didn't have to buy a lab book because I hand it out. And I'll do that this semester. Now, let me log into Blackboard, D2L. Let me go to student view. Now, everybody see Chem 170 and D2L on your screen? Probably not. Oh, yes, you do. All right. Now, if you go to assignments, you'll see the different assignments. Don't forget to hand in your signature sheet. But anyways, here I have the melting point lab, and I have it both as a MS Doc and also as a PDF file. You can do either one. Now I put the can scammer instructions every time. If you're all comfortable, though, I don't have to put that in there, let me know next week. But anyways, this is where you find the lab. And when you're ready, you submit it by clicking on here, and then you can upload it. I'm not going to do that. And this is how we do our labs. So it's time for today's lab. So one of the important things in organic chemistry, important physical parameter of an organic molecule, if it's a solid, is its melting point. And a melting point is when the temperature, a solid becomes a liquid, all liquid. The melting point of water, 0 degrees C. Now, inorganic molecules have a very sharp melting point. Organic molecules have a range. And let's look at today's lab. Let me just close something. All right, so here's today's lab. And like I said, melting points, crystalline organic have unique melting points. They're always lower than 300. By the way, I think salt sodium chloride melts at somewhere around 800 degrees Celsius, quite high. Inorganic compounds too. And this is important. There are 2 reasons organic chemists do melting points. And it either helps identify the identity of an unknown organic molecule, or it helps determine the purity. So 2 things, melting points and this is abbreviation for melting points. 1 is identity, ID, and 2 is purity. Now, a lot of organic compounds, they've already determined a melting point. So if you have an unknown compound, you'll run the melting point and see is it the same, and then it could be the same. Now, the melting point is a range at which a compound melts, begins to melt until the sample is all liquid. Now, you rarely have a sharp one, what I call but an organic sharp range is 1 to 3. So if you have compound X, and what you'll do is heat it up, and as soon as you see any liquid, that's the start of your melting point. When all the sample is liquid, that's the finish. So if, say, compound X, you see some liquid form at 92 degrees C, and it's all liquid at 94 degrees C. Therefore, the melting point for compound X is 92 to 94. And we use a digital, so you can actually sometimes get 3 significant, like 92.0 to 94.1. And that's melting point. Now, in this one, you'll be measuring melting points for some compounds plus an unknown. Now, here's a video I'll let you watch at your own leisure on YouTube. Now, the sample, when you put a sample into the melting point apparatus, because the definition of melting point is when you start and finish, you try and put as small a sample as possible. Because if you have too large of a sample, well, that's going to throw your melting point range off and give you bad problems or bad results. I wonder how that got blank. Anyways. And here I have a procedure. If you were really in the lab, you'd make a powder. If you have a solid that's not a powder, you'd fill it part way in what's called a capillary tube. And I show you how to tap it down to get to the bottom. You put it in the cool melting point apparatus. If it's too hot and it melts, guess what? You do it again. And you can use an airline to cool down your apparatus, and you start heating. If you heat too fast, you're not going to get an accurate sample. Melting points, determining melting points is one of those things that you have to show patience. You don't want it too slow because you don't want to be there all day, but you don't want it too fast, so you're not going to get accurate. And when a liquid, you see any, and you've got a light and a magnifying glass in the unit, you can say that's the start. And when the entire sample is done, then that's the end. And you're going to do a number of them. Now, there's something I have to teach you, and that's called the colligative effect. And the colligative effect is when you mix two chemicals together, what happens is the melting point drops down and gets wider. When you, even if they both have the same identical melting point, when you mix them together and take the melting point of that mixture, it gets lower and wider. Now, there's also, which we're not going to do in the lab for colligative effect, you have a boiling point elevation. And both of those, I'll teach you later on, are used in your antifreeze of your car. But for melting points, Remember, melting point, this is point. So because of the colligative effect, when you mix two different substances that are solids together, if they're different, you'll see a lower melting point for that mixture, and the range start to finish will be wider. Now you can use the colligative effect to help identify an unknown. How do you do that? UNK is short for unknown. Let's say you have an unknown and you have a melting point of the unknown is 80 to 82 degrees C. And you look up in the literature and you see compound Z has this melting point. Now, if you mix a 50-50 mixture of the two together, and the unknown is actually compound Z, you'll get the same melting point. Now, if unknown A is different than compound Z and you mix them together, then now the colligative effect will kick in and you won't get this melting point. It will be lower and wider. So if you take an unknown and mix it with a known and the melting point stays the same, then they're the same compound. If you take an unknown and mix it with a known and they're different, the melting point won't be the same. Well, in this class, if we're doing it in the lab, you would be doing the following. Let's look at. Now, I have a chart here for, this is called literature values. And if you looked up the literature value of biphenyl, it would be 70 to 71 degrees C. Now, since most of you would be rookies, in other words, I personally, I don't know how many, a couple thousand melting points I've done in my life. I've done a lot, especially in grad school. In my research for my PhD, I think I had about 145 new compounds that I made, and most of those were solids, a good part of them. I had to do melting points for my thesis and also publication. So each one of those I did 3 to make sure it was spot on, which that adds up real quick. But anyways, when you're new, your melting point is going to be slightly lower and a little wider than the literature value. Now, in the lab, and I have given you the data, this chart would normally be blank. And here biphenyl, notice it's a little lower than what they have: benzoic acid, transurea, and tranexamic acid. Now, both urea and tranexamic acid have the same melting point. Now, in the lab, if we were face-to-face, you wouldn't see this data. And I'd say one of the nice things about organic chemistry lab is you can find out, am I lying to you or not? I'm not, but who knows, I might. That's the beauty of science. You go in the lab and prove it. And you would have run a 50-50 mixture. Look what happened to the melting point. And these are actual numbers students have gotten. See how each one individually is identical? It's now much wider and much lower. Now, to make this fun, I have an unknown. And here is sample A. And when you do the melting point, this is the number you get. And in real life, I say pick one of A is one of these compounds from table 1. And just like I taught you, you would mix it with one of these. And if the melting point doesn't change, that's the compound it is. If it does, then it's not. Now, remember, you're new at this. So if you've been doing a slab, all your melting points are going to be a little lower than this. In this case, I give you the melting point with benzoic acid and the melting point with cinnamic, or I should really have tranexamic acid. And what you have to do, and this is one of the things for today's lab, and real life face-to-face right here, you have to write down the name of what you think unknown A is. And it's one of the compounds from this chart. Remember, colligative effect. If you mix two things that are different, the melting point will be lower and wider. If you mix two things that are the same, the melting point will be essentially the same. By the way, unless you've really done hundreds and hundreds of melting points like I do, if you do 2 of them in a row, you're going to be off by a degree or 2 in real life. Now, at the end of the lab, you'll see some questions, and you need to fill these out. Now, a couple of things. If you don't have a printer, just write down the table or the unknown. You're not putting in any data, and write the name of what you think the unknown is. Also, you don't have to rewrite the questions. Just put one and write your answer. Or if you have a computer and you can print it out, you can then scan it and set it up. Or with the Word document, you can just type in right in there. All those work. This lab is due next Wednesday. And so you can get your 11 points. Make sure you hand it in by next Wednesday afternoon. And with that, I'm done. Don't forget, tonight I have my office hour. If you have any questions, stop by. And with that, I'm going to say goodbye. Gehen gesund, be healthy. Don't forget, wear your mask out there. If you haven't been vaccinated, which I have, get them. They'll save your life. Even with all the new variations, if you get it and you're vaccinated, the odds of you being sick in a hospital are very minimal. Yeah, you'll be a little sick, but it's not going to kill you like you see in the news. So with that, we're done for the week because it's Wednesday because of the holiday on Monday. And once again, I'll say, gehen gesund, be healthy. Bye.